Hello, everyone. My name is Olivia Presidzio, and I'm a chemical engineering and computer science student at the McKelvey School of Engineering at WashU. Today, I will introduce you to an innovative approach to addressing a significant environmental and public health issue, antibiotic contamination in wastewater. Our focus is on leveraging zinc oxide nanoparticles, or ZnO, as a secondary wastewater treatment step to help combat antimicrobial resistance, or AMR. This talk models how ZnO nanoparticles in wastewater treatment plants, WWTPs, can help reduce antimicrobial resistance, AMR, in rivers. We'll first analyze the problem of antibiotic contamination in treated wastewater with a focus on the threat of AMR, before delving into the recent research backing ZnO nanoparticles as a potential solution to such contamination. Finally, I'll propose an implementation of this technology modeled on 5 wastewater treatment plants along the United Kingdom's Thames River, which is one of the most heavily antibiotic contaminated rivers in the world. Antibiotic contamination of waterways poses a growing threat, particularly as these contaminants contribute to the rise of antimicrobial resistance, or AMR. Antibiotic-resistant bacteria evolve by uptaking the antibiotic toxins and residues remaining in wastewater treatment plant effluent, as shown in this graphic. With all these bits and pieces of information, so to speak, on the mechanisms of antibiotics, the surviving of these bacteria are those which develop their very own mechanisms to fight back. In effect, resistant bacteria make infections previously treatable with antibiotics much more dangerous and deadly. To put this in perspective, the World Health Organization estimates that AMR could lead to 10 million deaths annually by 2050 if current trends continue. But that's not all. This issue isn't just a critical public health challenge. Drug-resistant bacteria are projected to cause economic damage on the scale of the 2008 to 2009 global financial crisis and push nearly 25 million people into poverty in the next few decades if no action is taken. Current wastewater treatment systems, while effective in removing many pollutants, often fall short in eliminating pharmaceuticals, particularly antibiotics. Through processes such as primary sedimentation, biological aerobic and anaerobic treatments, and secondary clarification, these facilities are primarily designed to remove organic matter, pathogens, and nutrients, not the complex chemical compounds found in many modern drugs. As a result, a significant amount of antibiotics remains in the treated water, eventually entering rivers and lakes. This residual contamination fosters an environment where bacteria can develop resistance, further compounding the AMR problem. ZnO nanoparticles present a promising solution to this issue. The latest research by Dr. Telekozani's team, titled Comparison of Azithromycin Removal from Water Using UV Radiation, Iron-6 Oxidation Processes, and ZnO nanoparticles, has compared the 2 most common current treatments for antibiotic removal to the latest zinc oxide nanoparticle development. In short, UV radiation has a relatively low but inexpensive 47% removal efficiency of antibiotics. Iron-6 oxidation has a better but very costly removal efficiency of 71%, and zinc oxide nanoparticles have a whopping 97% removal efficiency for a similar cost to UV radiation. Where UV radiation requires a large surface area and iron-6 oxidation requires the purchase of expensive materials, zinc oxide nanoparticles are not only cheap, but they are also relatively compact and, most importantly, strikingly efficient. This unique combination of high removal efficiency and lower operational costs makes zinc oxide nanoparticles a viable option for large-scale water treatment applications. Zinc oxide nanoparticles remove and degrade antibiotics in water through a photocatalytic process. This process begins when zinc oxide nanoparticles absorb UV light, which excites electrons from the valence band to the conduction band, creating electron hole pairs. These pairs are crucial for the next steps. The electrons reduce oxygen molecules to form superoxide anions, while the holes oxidize water or hydroxide ions to produce hydroxyl radicals, as shown on the right. Hydroxyl radicals are a highly reactive oxygen species capable of breaking down the chemical bonds in complex antibiotic molecules, like azithromycin shown here, leading to their degradation into harmless end products like carbon dioxide and water. This mechanism is influenced by factors such as the intensity of UV light, particle size, pH of the solution, and the presence of other substances in the water, of course. But it is the photocatalytic property of the zinc oxide nanoparticle degradation reaction which makes it such a versatile, cost-effective tool for reducing antibiotic pollution in wastewater. All you need is some sun. To model the feasibility of adding a zinc oxide nanoparticle treatment step to current wastewater plants, data from the UK State Department for Environment, Food, and Rural Affairs was chosen for the breadth of data available, as well as the critically high levels of antibiotic concentrations in River Thames. The 8 antibiotics tracked in the image at left are the most common antibiotics prescribed globally. Many of these are drugs you've likely taken at some point, such as azithromycin, clindamycin, and ciprofloxacin. Their concentrations in downstream River Thames were tracked over the course of a year and plotted using a cubic spline best fit curve in MATLAB, revealing the statistically significant seasonal fluctuations of the antibiotic concentrations. With over twice the antibiotic concentrations in the winter than the summer months, this introductory implementation chose to model a 6-month on, 6-month off treatment operation cycle to simultaneously maximize the quantity of antibiotics being degraded and minimize the operational costs following the initial capital investment. Adding any wastewater treatment step is a costly endeavor, but by phasing ZnO nanoparticle treatment into use when antibiotic purification is needed most in accordance with seasonal oscillation, the operational costs can be halved while maintaining a high annual percent antibiotic removal. This integration involves adding a zinc oxide nanoparticle treatment step after conventional secondary treatment processes like sedimentation and sand filtration, as shown here in 2 synonymous secondary treatment processes. Coupling this addition with chlorination would ensure that residual antibiotics are effectively removed right before the water is discharged, allowing the current methods to operate unaltered for minimal installation downtime. As far as cost goes, the 3 equation system shown here was simulated based on 2023 market prices of zinc oxide nanoparticles and hydrochloric acid. This hydrochloric acid was used for adjusting pH for optimal removal efficiency, as well as the operational cost approximations published in Turkey's Design and Cost of Solar Photocatalytic Systems for Groundwater Remediation. While the details of these calculations are beyond the scope of this presentation, the modeled rough costs were found to be surprisingly within reach. After the initial capital investment of about $350,000, it would only take about $70K to run the treatment for half of the year. And that's across 5 treatment plants along River Thames. Notably, if this cost of $70,000 a year becomes an obstacle to implementation, simply phasing the treatment in 1 plant at a time, or even for 1 month, then 2, then up to half a year at a time, can still drastically improve the antibiotic concentrations in River Thames. Reducing these concentrations to levels deemed safe for public health, at the very least, is a large feat, but every small step counts. While our research has demonstrated the promising potential of zinc oxide nanoparticles for antibiotic contaminant removal from wastewater, there is still very much to learn. A preliminary list of action items is as follows. 1. The zinc oxide half-life, or rate of consumption decay, has not yet been documented, and this model was based entirely on the batch-by-batch processing modeled in the bench experiments in Dr. T's work. A continuous flow model will surely make for a much cheaper, faster, and more efficient process flow when zinc oxide is recycled. 2. Zinc oxide costs can be reduced by utilizing a thermal production reaction that would allow wastewater treatment plants to effectively recycle reaction products as precursor chemicals required for the on-site synthesis of zinc oxide nanoparticles, at thereby a much reduced price. The simplicity of the zinc oxide reaction mechanism will make this development relatively easy, as there are no byproducts that would go unused or need to be filtered out. 3. The pH costs can be easily avoided with a systematic linkage between the acidifying chlorination purification step and the basic zinc oxide treatment step to achieve the optimized pH of 6 for highest zinc oxide adsorption efficiency, without spending another dime on hydrochloric acid. 4. Lastly, on the environmental side of this analysis, monitoring the long-term impact of nanoparticles on aquatic ecosystems and exploring the potential for downstream recovery and reuse of nanoparticles can make for a more sustainable, cleaner River Thames and UK wastewater treatment process. In conclusion, zinc oxide nanoparticle treatment represents a promising solution to a critical problem. By integrating this technology into existing wastewater treatment processes, we can significantly reduce the levels of antibiotics in our water systems, thereby protecting public health and the environment. To reiterate, the key benefits are as follow. Superior efficacy. Zinc oxide nanoparticles remove up to 97% of antibiotics from water, far surpassing traditional methods like UV radiation and iron 6 oxidation. Environmental stewardship. By preventing antibiotic pollution in natural water bodies, ecosystems remain protected and biodiversity allowed to flourish. Cost-effective implementation. This technology can be seamlessly integrated into existing wastewater treatment systems, making it a scalable and economically viable solution. Leadership in innovation. Adopting zinc oxide technology will position the UK as a leader in environmental sustainability and public health protection. The time to act is now. I urge stakeholders, including government agencies, environmental organizations, and the scientific community, to support further research and implementation of this technology. Together, we can make a significant impact in the fight against antimicrobial resistance. Thank you for your attention. I now welcome any questions or comments you may have about the research, the technology, the modeling, or any of the potential applications. Let's have a discussion on how we can work together to address this pressing issue.